Right, hello guys. So in this, what we're talking about again is static equilibrium. And the difference here is we're including friction for one thing. And the other thing that we're doing is having the plane itself perhaps being on an angle or on an incline, really is what we call it. So in this situation here, this question, first thing I'm going to do is going to draw a diagram. So I've got a book resting on a rough table, okay. The book is of mass 2 kilograms. There we go. It says when a force of magnitude 8 newtons acts on the book at an angle of 20 degrees to the horizontal. Let's do that then. So that means we've got this force acting like that. It's 8 newtons, and that angle there is 20 degrees. That's how we'll draw that. The book is on the point of slipping, so there's a frictional force that hasn't come out great, that, but you know, that's where the 20 degrees is to that horizontal there. Go on, I'll put that in a little bit more, maybe. Yeah, that looks a bit better. So the book is on the point of slipping. There's a frictional force acting backwards. Okay, the only other force that's being exerted here is with the normal reaction force. So there's a normal reaction force there, sort of, I would say, stopping the book, you know what, sliding through the table, I suppose. Right, okay. Now, just like we've done with other questions, your job here is to resolve in 2 directions. So we're going to resolve vertically and horizontally. The other thing I'm doing here, I'm sort of reading through the question, and it says there, look, calculate the value of the coefficient of friction. So I want mu. So in my mind, like in my toolkit, maybe I'm thinking I'm going to use F equals mu R. That's what I'm going to use. So that's what I'm going to be aiming for to find mu. So in order to use that, then I want to know what F is and I want to know what R is. So looking at that picture there, yeah, okay, I understand what it is that I'm going for. Right, so let's resolve in one direction. I'm going to go for horizontal, and the reason I'm going for that, just like I've said, is I just find it easier to resolve this force horizontally because it's the adjacent, so it's going to be cos. So let me do that then. I've got 8 cos 20, take away F equals 0, and then I can work out F just there straight away, can't I? So F equals, let me do it then, just 8 cos 20, that's it. 8 cos 20, 7.5, there, 7.52, I'm going to say. So F equals 7, no way, 7.52, straight in that. So there we go, 7.52 E. But anyway, okay, now let's resolve horizontally. Having resolved horizontally, let's resolve vertically then. Okay, so I will. Right, what's going upwards? We've got R, and we've got the vertical component of that. That's going upwards. So they're both positive. And then what's going down is the 2G. So go on, I'll do it then. I've got R plus, yes. No thinking to do here. That says 8 cos 20. So this is going to be 8 sin 20. No thinking whatsoever. 8 sin 20. Take away 2G. Why take away? Because it's going down. Equals 0. So then R equals, I'm going to move them over. I'm going to be careful with the minus signs here. It's minus signs that do you in. So 2G minus 8 sin 20. Let's work that out. So 2 times 9.8, take away 8 times sin 20 equals, there we go, 16.86. I'm going to write 16.9, 3 significant figures. So that's it then. Because I know now, here, F equals mu R. Oh, why is it F equals mu R? Why is it not F is less than or equal to mu R? I'll tell you why. Because it says here, it's on the point of slipping. Oh, where is it? There, on the point of slipping. So that means F equals mu R. It's limiting equilibrium. So I'm going to use then F equals mu R. So 7.52 equals mu times 16.9. So then mu equals, let's work it out. So 7.52 divided by 16.9. And there we go, 0.44. Yeah, 0.44. I'm happy with that. Right, that's it. Okay, so that is how to do that question. I'm gonna plow straight on now and do another question. But as I said, like, you know, please do pause the tape and have a go with that yourself and have a go with similar questions. Meanwhile, I'm gonna, let's see. Right, yeah, okay. Right. Let's do like this one. This is a tough one, this. Okay, the picture's already drawn there. Okay, I'm conscious that the words aren't dead clear. Let's see. Yeah, a bit better. Okay, so I can see we've got I'm going to draw my own picture. So there it is. Remember I said, try not to make your angle look at all like 45 degrees. And I said that with a specific reason of making it easier to decide whether it be sine or cos when you're resolving. So there's my particle. It's a mass 1.5 kilograms, so 1.5 g directly down. This force X is going straight up. Okay. What else is there's a normal reaction force. Now that is at right angles to the plane. Okay. So it's not vertical, is it? It's at right angles to the plane. So it's going up at that angle. Okay. And then the other force that's on it is friction. Now, friction opposes the motion. So this particle, it says, and this is crucial, this particle, let me get my highlighter. Okay, this particle here, it says is, what is it? It's on the point of moving up the plane. So it wants to move up the plane. Therefore, the friction is acting down the plane. Friction's going that way. So my frictional force is that way there. And that's all the forces that are acting on it. It's a bit of a nuisance the way that X is there. I wasn't much preferred it to have been there, but it isn't there. So, you know, let's just get on with it. Like, having done that then, right, we want to find the normal reaction. We want to find R and we want to find X as well. Okay, so I'm going to do, I'm going to firstly find the angle actually. So when I'm looking at resolving, so that force is perpendicular to the plane. They're both parallel to the plane. That's the direction in which I'll be resolving. I'll resolve parallel to the plane and perpendicular to the plane. The only force that's in nuisance here is this one. Okay. And I want to know, can you see that a little bit? You kind of want to resort it a bit heavier. I want to know that's a right angle there. I want to know what this angle is here. Okay. Now, how do I do that then? I look firstly at this right angle triangle, and this right angle triangle tells me that we've got 65 degrees there. Okay. In it, look at the right angle triangle there. Yeah, 65 degrees. Okay. Right now, I'll look at this angle situation here. I've got 65 degrees there. Therefore, that must be 25 degrees. Okay. So there we go. Right. So that's 25 degrees there. Right now, I'm in a position now that I know the angles on the 1.5 G force. That's supposed to be a straight line, that, guys, and it doesn't look at all like a straight line. So I apologize there, but that's supposed to be a straight line. That's way off. But like, yeah, sorry about that. But that's what you're doing. You know, you yourself are drawing a straight line on from R in order to be at 90 degrees to the plane. Right. Let's resolve perpendicular to the plane then. Why? Well, we have to do both. You might as well start with one. But I want to do the one what's cos. So this is the cos one because it's adjacent to it. So I'm going to go that way. So if I resolve perpendicular to the plane, okay, then what? Okay, I have R minus this component, the components of the 1.5 G force that's going straight down. So minus 1.5 G cos 25 equals naught. Okay. Yeah, that's it. All right. So therefore, R equals, I can work that out straight away. R equals 1.5 G cos 25 Let's work it out then. So 1.5 times 9.8 times cos 25. There we go. 13 points. I'm going to be a bit less cavalier about the decimal point places here. 13.32. Okay, I'm going to 4 there, so I can round confidently to 2 or 3 later. So that's oh no, do you know what? No, I mustn't. No, wrong. I'm going to say 13.3 because that's an answer. So that's an actual question that it's asked, hasn't it? What is R? And I mustn't go to more than three significant figures because the question involves G. So there's R there anyway, 13.3 newtons. Now, find the value of X. Okay, well, in order to do that then, I'm going to resolve, what's that? Parallel to the plane. Okay, so having resolved perpendicular to the plane, now let's resolve parallel to the plane. Okay, so what have we got? We've got X going up. We've got F going down. And we've got a component of this force also pointing in the down direction. So it's minus, because it's definitely not pushing it up, is it? It's pointing it down. So minus 1.5 G. Now, is it sine or cos? No thinking at all. No thinking whatsoever. I can see that the one before was cos. So therefore, this one is sine. So 1.5 G sine 25 equals 0 because it's in equilibrium. So F equals, not F, X equals F plus 1.5 G sine 25. And at that point, I might stop and go, I'm at an impasse. I can't get any further than that. Well, yes, I can, because I know that F equals mu R. So go on then, let me work out using F equals mu R. How is it all right for me to use F equals mu R? Because it says, where is it? It says it's in limiting equilibrium. So F equals mu R is all right to use. So actually, I'm going to go up here, out the way, and then I'm going to return to there in a minute when I know F. So F equals mu R. And, you know, do this yourself in an exam. When the examiner's marking your work, you know, they're looking for your work. It just doesn't matter where it is. But I want to put that F in that equation in a minute. So I'm going to work it out here. So F equals mu R. So F equals, what's mu? 0.25. So 0.25 times what I got for R before, 13.3. So 0.25 times 13.3. So there we go. Just times that by 0.25. 3.33 it reckons. So F equals 3.33. Okay. And then X, let me just throw that in then. So X equals 3.33 plus 1.5 G sine 25. So there we go. Add 1.5 times 9.8 times sine 25 equals 9.54. So that's my answer. 9.54. And I'm happy with that in terms of significant figures because 3 is all right. That's it. That's a hard question. That it's valid in terms of it being an exam question. The only thing I would say, right, the only thing where I might think there's a little bit of a simplification from that being a bona fide exam question is I'm not sure whether in an exam they would have asked you A first. I think they might have just said calculate the value of X, and you yourself, you have to know that you need to work out R so that you can work out F, so that you can work out X. Like it all links in. Okay, right, again, do please pause now and have a go, you know, or go over like what I was on about. Oh, where did that F come from? Oh, how is that 25? You know, do all that, do all that. It's all good. While I'm going to go on to now a really hard question. Okay, so have a look at this one. This is tough. This is as tough as they come. And right, again, well, not again, but in the spirit of what I've just been on about in terms of, look, an exam might just ask you just one thing. Look here, big mad question where all this, and then the question is just find mu. That's all. Okay, halve that, and you've got to know what you're doing. And again, in your toolbox is going to be F equals mu R. Okay, so let me write that down because I'm gonna do it. And actually, F equals mu r is very frequently worth a mark in the exam. Just, well, not really stating it, like using it though. But yeah, there you go. Right. So let's sort the diagram out. I don't know whether I'm quite happy to use their one. Yeah, go on. I'm going to use their one, then won't run out of space here. But I'm certainly going to add on to it. So what have I got? I've got 1 kilogram there. So 1g. I'm just going to write G. Don't really like that. I wish it was some number, but it isn't. And then I'm going to, well, what else have we got? We've definitely got a normal reaction force. Okay. Yeah, let's use a ruler. Okay. Yes. Nice one. Okay, I put that like proper at 90 degrees there, really accurately. So that's R. Okay, and then I want to carry that on a little bit, don't I? And this is what I'm on about, guys. When I say try not to let your diagram be at 45 degrees, and I'll tell you why. Because here's the previous one. Look, that there, it was either going to be 65 or 25. It's very evidently 25 when I draw it like that. Whereas on this one, man, I'm not sure if that's going to be 40 or 50. Like this one here, it's either going to be 25 or 65. It's certainly not 65 because look at it. Like of course, it's not 65. But on this one, it's a bit hard to tell. So that's my wise advice. Please draw your diagrams so that they're not or anything looking like it's all 45 degrees. But anyway, let's go through the process. That's 40 there. This is like a right angle triangle. So therefore that there is 50. So therefore this angle here, I'm going to draw it like properly in like pen. I mean, that's 40 there. So that's 40 degrees. Okay. And that's it then. But it's harder to tell in that case because the diagram was, you know, at 40 degrees. Right. Okay. So we've got this 10 newtons here. And what else does it say? It says, right, it's in equilibrium. I'm going to highlight this again. This is very important. It's on the point of moving up the plane. There we go. So what does that mean? That means the friction is opposing the motion. So therefore, the friction is acting down the plane. So the friction is acting that way. And that is all the forces we've got on the box. Okay, on the particle. Okay. What was I going to say then? Oh, yeah. What makes this hard, though, is the fact that this isn't just up the plane. This is at some mad angle, its own extra angle. So it just adds a layer of difficulty. But, you know, so what? Let's do it. What are we going to do? We're going to work out R, and we're going to work out F, and that's it. Okay, that's what we're going to do, because then we'll be able to find mu then. So how are we going to do that? Resolve. That's all we're going to do. Resolve. So if we resolve, I don't mind. Let's do these are both a bit of a nuisance actually, and you'll see why in a sec. But I'm going to say let's resolve perpendicular to the slope. Really, no reason whatsoever. We have to do both. Might as well start with one. Let's resolve perpendicular to the slope. So we've got R going up. We've got this component of G going down. Now what is it? It's G cos 40. Okay, that's the adjacent. So it's G cos 40. So minus G cos 40. But now, what else have we got? We've got this guy has a component going up the slope as well. Sorry, not up the slope. It's got a component going perpendicular to the slope as well. So we want to know what the component of the 10 is up there. And I'm going to say, so it's plus, because it's in that direction. Is it 10 cos 20? No, it's not, because 10 cos 20 is adjacent. So 10 cos 20 is in that direction. So it must be 10 sine 20, which is that one there. And it is, because if I complete the right angle triangle, really shaky hand there. If I complete the right angle triangle, that's what I want, that component there. And it's going up, it's going in that direction. So yeah, plus 10, 10, 10, yeah, nice one. Sine 20 equals 0. And has that found me R? Yeah, it has. So R equals, careful of the minus signs, G cos 40 minus 10 sine 20. Let's work it out. Okay, and it tells us what R is then. So what have I got? 9.8 times cos 40. Yes, close your brackets. Take away 10 sine 20. There we go. 4.09. No, I'm going to go for this here. 4.087. Okay, just an extra little significant figure, just to make sure my answer's all right. What else? Well, no, you know, no thinking whatsoever here. Resolve parallel to the slope then. Okay, so what is the parallel to the slope? Well, going up in that direction is the 10 cos 20. I just spoiled it there. But it's 10 cos 20 because that was 10 sine 20. So this has to be 10 cos 20. It's in a perpendicular direction. Okay, well, 10 cos 20 is going up. F's going down. It's going down the hill. Right. And then what else is going? What about the G? That's going down the hill as well. And there it was G cos 40. So here it's going to be G sine 40 equals 0. And I can work out F now. So F equals, what have I got? 10 cos 20, be careful of the minus signs. Take away G sine 40. Yeah, that's it. Work it out. Go on. Okay. So 10 cos 20. Nice one. Close the bracket. Take away 9.8 sine 40. Close the bracket. Equals, yes, 3.0. I 8 rounds of me. 098. Okay, right. So that's it. Yeah. Is that it? Yeah, that is literally it. All I need to do now is put F equals mu r. So I've got 3.098 equals mu times 4.087. So therefore mu equals, and I'll work it out. So divided by 4.087 equals, there we go, 0.76. And I'm happy with that. Two significant figures will do me. Any units? No, there isn't. The mu's just a coefficient with no units. It's a well, I was going to say a constant. It's absolutely not a constant. It's a coefficient. The dimensionless is the word after. It's dimensionless coefficient that just tells you how slippy or anything a surface is. That is one of the biggest mu's we've come across. It's not as big as they get. It can go as big as you want, but normally they are a bit smaller than that. But it's all right. It's not unreasonable, and I don't think you'd be put off by that. That's it. Right. I said this was a hard question, and I mean it. I wasn't exaggerating. This is a hard question, and if you can follow that, and then 2 questions that are like that, then really well done. But do have a look through and see what I've been on about there. But right, that's all I'm going to say. Okay.